Hello, everyone. Thanks for taking your time to join this session. And this is a pretty good evening to meet you all online. And we have Ambarish Ganguly here about his professional what he does and all those things. Dan his professional life. He's a very interesting guy and an active person and a learning person, and also even at this point of time he's very interested to present and share his knowledge to the community. That is a very great thing. As a youngsters, we should learn from him. And yes, thank you so much, Ganguly. Today we are going to Ganguly is going to present a talk about how to create a recommendation engine using text, cosine similarity, and word embedding, and how to publish that into Azure ML. So he'll be walking us through a demo as well. Thanks a lot for accepting this opportunity, Ganguly. Please go ahead.
Yes, thank you, Dinesh, for the very generous introduction. So, Dinesh, can I see who is there in the live thing?
Uh,
The guests?
no, no, Ganguly. Actually, we can see our guests in the YouTube only. But
Okay, okay,
the chat, the messages, I'll just keep you posted if there is any questions. So
okay.
yeah,
But
that's
YouTube, we are streaming in YouTube, right?
yes, of course.
So what is the link in the YouTube? Let me also open up YouTube so that I can see how many are have joined and so on and so forth.
Yeah, I'll just
You
give
you
you.
go ahead. You go ahead, and then I'll start in the between. Okay. Okay. Thank you, everybody. I hope you are able to see my screen. So this talk is about Azure ML recommendation engine using text, cosine similarity, and word embedding. So what we will do here is that we will start from the scratch. We'll build a very simple recommendation engine using text data, and we will use the concept of word embedding. Okay. So before that, I would first state the problem before we go into anything. So we are trying to do recommendation for questions which have been asked by a student. Okay. So, and what we are trying to do is for a community. So this community is called Career Village. Okay. So Career Village is a community where students get free personalized career advice from real professionals. So how does it work? So it works like this. A student asks a question, and then what happens is that there's this site which is there. Let me just show you also the site. So the site is here, career village. So this is a site in which they can ask questions. Okay. So what they will do, they will ask a question, and this site will route the question to certain volunteers who are professionals. Okay. And then the professional will answer the question. So how does this happen? Is that see, suppose you ask a question, how to remember lines of code. Okay, this is a computer programming thing. So it will come to a person like me who is working in computers. It will not go to a person who is an expert in golf or music, right? The next question is, how do I become a music artist? Obviously, it should not come to me. I don't know much about music. So it will go to somebody who is good in music. So here what happens is that the questions will route it to the correct person. It is not done by rules, but it is done through some uh, intelligence. So that we will see by a recommendation engine. You are using recommendation engine every day. You are using it in Flipkart, you are using it in Amazon, you are using it in Swiggy, Zomato, everything. If say I order say Chinese food in Swiggy, it will say perhaps you may order like this. Or if I order from Amazon a business book, it will say, since you have bought say the have read the range, can you please read Atomic Habits? So there is a similarity kind of a thing. So we are using it. So today in this lecture, in this session, what we will do is try to understand a very simple one. So this is something about the recommendation. So this is about the career village. So there are almost 500 students for every guidance counselor in US. I do not know in our country, India, how many counselors are there. So it is very difficult for the counselor to answer the questions. So what they do is that the careervillage.org needs to be able to send the right questions to the right volunteers. Now, what this is from a Kaggle competition. So what they wanted is that I participated in that Kaggle competition. I did not win anything, but I learned a lot. And that is why I'm going to say what I learned. So develop a method to recommend relevant questions to professionals who are most likely to answer them. So just as I gave in the example, music question to a musician, computer question to a computer engineer, deep learning question to a deep learning expert, and so on and so forth. And a biology question to a biologist, a zoology question to a zoologist, similarly. So what we will do here, I have modified the uh, problem statement a little bit for our demo here. So what I have done is that there are many files. So here, so they have questions, they have answers which have been given previously, and they have got professionals. So what they would do, if you give a question, who is a professional that they would like to route the question. Now, what I have done is that in this, I'm not getting the professional into the picture. I'm saying you give me a question, I will find you an appropriate answer from the question that you have asked. So, say suppose you ask me that I want to be a data scientist. What should I study? Okay. Then what we will do is that we will find and search from the existing answers, existing questions, that this question is similar to which question in my base, in my knowledge base that I have. So this data is available with me. There is a question set, there is an answer set. So I will search, I will not do a search, I will try to do something to find similar questions. And then I'll get the top n, which are the top similar questions, and find the corresponding answer and display the answers. So that is how I am going to do. Okay. So it would be like this. Like I want to be a data scientist. What should I study? I click on this button, and then this will appear. Hello, Chong. Blah blah blah. This is one answer, and so and so it would go. Okay. So how do we do it? So there are several techniques in which. So this is text data that is coming in. The questions are text data, right? So so what would happen is that I have to convert the text data into numerals. Why? Because otherwise the computer does not understand, right? So what, there are several techniques. One technique is called the one hot encoding. It means if you have this sentence like the cat sat on the mat, what I will do is that I will take each word and I would say one for the and all others are zero. And there are many words in the English vocabulary. So there will be lots of zeros. So you can imagine that this technique is not that great. Why? Because this matrix that we are forming is going to be very large with lots of zeros, and manipulating the matrix would be very difficult. So this technique, though it is one of the techniques, is not a great one. So this technique is called one hot encoding. Why it is called one? Because only one has is hot and one hot encoding is there. Another technique is called label encoding, in which we have the words and we will give values to the words, and maybe we'll give the other one, two. So there would be many words and we would give these values to these words. This is also not that great. We have solved the problem that it will not be that big, but it is losing the context that whether the is similar to cat or not, or something like that. That information is not there. So the next technique is called the word embedding. Okay, so the word embedding, so what the people have done, like there are many uh, companies like Google who have trained terabytes and terabytes of data, and what they have done, they have created a vector, but this vector is dependent. So it can be a 100 feature vector, or it can be a 300 feature vector. So there they have values for each of the features, and what it does is that it makes that it makes sure that the words which are similar are closer to each other. So so what I would do is that, let me just go back and see if there is something that I have done before. Let me try to find out. I have a very okay. So here see I want to give you a feeling of this word embedding. So here I'm using Spacey for word embedding. So so Spacey, it is using something called glove, which is I think by some Google or somebody. They have trained a large corpus and made sure that we have got this vector that I was showing. Okay, so let us run it and see, and I'll give you a demonstration. So it is taking some time. While it takes some time, I'll just explain what is happening. So I'm loading this large model to get the vectors. And I just want to show you of how large this vector is. So it is around 684,000 words are there in this. So it is 684. So if I just, okay, it's still loading. So let it be there. So there are 684,000 words in it, and the shape of the vector is around 300. Okay. So while it is taking some time to run, it is quite a big thing. Let me just try to refresh it. Okay. So, okay, now it is fine. So it is 684. So here, let's choose one word. So here, if I choose a word, say queen, so you see that there is a vector of 10 numerals here because I have 10. If I do the vector shape, you see that there are 300 features of it. Now, here's the thing. We are trying to find at how similar the words together. We'll explain a little bit later what is cosine similarity. Cosine similarity denotes that how close these two vectors are. Queen and king. See, it is a cosine similarity is 0.72. Queen and mother, it is 0.44. Queen and princess is 0.65. So what is the feeling that we are getting? The cos of any angle is between -1 and 1, right? So if it is very close to each other, it will be 1. And if it is absolutely opposite, it is -1. But if it is orthogonal, it will be 0. So I'll come to that. So, but you see here, the queen and the king is 0.72, which is highest. Next come the queen and the princess, and then the queen and the mother. Okay. So this is the similarity. So because of word embedding, we are able to get the, what should I say, get the similarities here. Similarly, I have a sentence, say, I am a software consultant, hey me data guy, and hey me plumber. So these are the different vectors that is there. So for each word, there is a vector of 300 character, 300 features. For a sentence, what it does, the spacey, this vector, what they do is that they make an average of these. So that might be not a great thing, but at this moment, since it is a very simple example, it's okay. There are many advanced now models now, BART and all these things, which are much more efficient, but here it is just taking the average. So here also you see the shape of the vector is 300. So here you see with x1 and x2, the similarity is 0.73 738, and for x1 and x3, which is a software plumber, it is 0.64. You see that this similarity between software and data guy is more. So what I'm trying to impress upon you is that this technique shows of how similar these things are. Okay, similarly, I have made some more fun examples. So I have chosen Pepsi, Coke, Sprite, chips, potato chips, and teacher. So here Pepsi and Coke, you see the similarity is 0.665. So if I run it here, Pepsi and Sprite 0.39, not very similar. Coke and Pepsi similar. Pepsi and chips absolutely not very similar. Pepsi and teacher absolutely no way. They're not related. Minus 0.009. Pepsi and potato chips 0.29, which is higher than Pepsi and chips. So that makes it, so that's what is about word embeddings. I will jump on to something like the cosine similarity. So here, what is cosine similarity? So we said that that sentence is a is like a vector. So we all know if it is in a two-dimensional space, the vector is having two values. Okay, it is having two values. If it is in a three-dimensional space, it is having three values. Till this point, we can imagine as humans, but I do not know of anybody who can imagine more than. So if it is a four-dimensional space there, so each point will have four values. If it is a five-dimensional vector, it will have five values. But our sentence will have 300 dimensions. So it is a vector of 300 points. Let's not go into to visualize, but if you understand that it is a vector with 300 points denoted by that. So when we denote what is the similarity, we are measuring the cosine between the two vectors. Cosine between two vectors is 0 because cos 90 is 0. These two vectors, it is 0. So if you are very fancy with maths, it is a math is a dot b, which is the vector dot product, and by the norm, L2 norm, a multiplied by b2 norm, which is a very fancy way of saying that ai bi, and then you sum it over. And then another fancy way of L2 norm is that a dot a square, then you do a sigma of that, and then you do a square root, which is all fancy way of seeing all these things. But if you like to do it in code, I'll show you of how we can do it. It is very easy. Say suppose this is a four-dimensional vector, right? So what we do, A is this vector, B is this vector, and A dot B is 1 star 1, 0 star 1, 0 star 1, 1 star 1. Add it, this one. A L2 norm, which is very similar. 1 star 1, 0 star 0, 0 star 0, 1 star 1, and then sum it over. Sum, this is a sum, this sum, and then I do a square root, np dot square root. Similarly, b2 norm, and then this one is a dot b by al2 norm star bl2 norm. I just wanted to show you that this, you don't have to know all these things, but if suppose you do not have a library like Python or some, and you someday want to write your own recommendation engine, maybe say in some language which does not have this capability, maybe Rust or Golang, Julia or something, so this might help you. Okay, so what I'll do is that I'll take a pause and then I'll go into the actual problem. actually. So let me just take a pause and see if there are any questions. No questions till now. Okay.
As of now, there is no questions,
Okay.
Amrish.
Okay.
If
Okay.
there is any,
Okay.
I'll just heads up, give a heads up to you.
Okay. Okay. But if suppose you want to ask any question, please feel free to type in. This is a logical time to take a pause. So what I will do is now that we will go to the next part, which is the Azure ML part. So here what we do is that in the Azure ML, I have already done the. So before we go into the Azure ML part, let me explain you what I am doing. So this is a training script. Okay. The training script, I will go into the Azure ML, but the core, I will tell you what we are trying to do. The core is something like this. The core is that I am reading the questions. It is a questions.csv, which I have it here. Let me go to the questions notebooks. Oops. So these are the questions which are there. Questions are there. So this is a question, and this is a questions question body. Okay, so this is a question body. Okay, so this is a questions. So I am reading the questions. I am reading the professionals. I don't need it maybe, but I am reading it, and I am getting the answers also. So the answers are also here. It might take some time to open. Let's see whether it opens fast or not. Oh, it opened fast. So there is the answer here. So let's go back here while. So I'm reading the questions, professionals, and the answers. Then what I'm doing is that I'm merging the professionals and the answers together, and then I'm merging the professionals' answers and the questions. So that what happens is that I have a complete set of the professionals' questions and answers together. So for each question, I have the answers together. Then what I'm doing is that I'm removing which do not have a title or which do not have a body, and then I'm making one variable with the title and the body, and then I'm cleaning the text, which is very simple, which I'm just making it lower and removing the punctuation and all these type of things. Then what I am doing is that I am downloading Spacey, and what I am now doing is that I am creating for each question the vector that is there. So for each question, now I have something like this. Something like 300 columns. So this question one, I have a 300 feature vector. Okay, just like the one that we did here, just like the one that this is a question, and I have a 300 feature vector. So once I have the feature vector, what I am doing is that I am doing a pickle.dump and saving it to a pickle file. Okay, so this is the thing. And then why am I doing it? So when we will see later is that when the question comes in, what we will do is that we will take the question, and then for every question in my base, in my pickle file, I will do a cosine similarity. And now after I do a cosine similarity, I will pick the ones which are highest. We will see that. But for Azure ML, so this is very compute intensive, we want to use a cloud. So what we will do, we will push everything into the cloud and we'll do the processing in Azure ML. So that is what we are trying to do. And now what we are doing is that we are starting from scratch in Azure ML. So that was the core, the heart of the problem. So in Azure ML, what I have done is the first step in Azure ML is create the workspace. So to create a workspace, you have to give name, subscription ID, resource group, and the location. So if I go to my portal, I've already run it because it takes a lot of time to complete this thing. It took me around an hour to run all these things together. So I have run it for you. So I have created this workspace, Azure ML workspace. Okay. So this workspace that is there, if I launch the studio, so I can find that this is my workspace which I have created. Okay. And now what we do is that once the workspace is created, another thing, it provides a key vault, storage account, and all these things are created in the workspace. So we can see it here also. If I go back here, if I go to home, this is my resource group. And if you see my resource group, don't consider the AKS cluster right now. We will come to that. This is a workspace, but you have the application insights, key vault, container registry. So container registry will come later. Key vault, storage account, and these application insights are created now. So I have got the workspace, and now what we will do is that, so this is a home of everything. Okay. Now what we will do is that we need the data, right? So what we do is that we upload the data into the data store. So what data we have? So we were showing you, right? We have the questions, answers, and these things are there. So what I did was that we uploaded the data into the default data store. So where is the default data store? If I go here, the data store is here. The default data store is this. And if I go here, if I go to the account, if I go to the containers, if I go to the data store, you can find that this is the one where I have put everything over here. Okay, so that's all done. So after this is done, what I will go here is that I'll create a training folder so as to put the code. And then what I do is, because I want to train it not in my machine, right? Here I have the flexibility, since I am doing it in Azure. I just created a compute cluster, and that is, I have made it only one node, but you can make it more nodes. You can create a very large machine. I've used a standard D2V2, and I have created a compute target here. So this is how you can create. So what is happening is that you are not doing it in your machine, you are pushing it into the other machine. And then what we do is that we created the training script. So this is a training script that we have created. The only difference when we are running it in this Azure is that we will have the argument, the data folder coming in. So the data is not in my local machine, right? So I have to pass the data folder. So that is what is coming in as an argument, and we will use it as the argument when we are reading it. Okay, so this data folder will be coming as an argument when we are doing it. So this is the only difference. And then we create the environment. So what is the environment? The environment is something like, so this script requires these packages, the scikit-learn, spaCy, pandas. Okay, so this is what we are defining as the environment. These are getting the environment is being created through that. Then we register the environment in the workspace. And then what we do is that we create the estimator. So what is the estimator? The estimator is something like we created till this point, we have created the compute, which is the machine. We have created the environment. We have created the script, and we have the source directory. So this all combines it together. Okay. So this is the estimator we have created. Now what we do is then we create an experiment. So the experiment we create, and it is within the workspace. So if I go here, we can see this is my experiment, the Reco experiment. And we can, in the workspace, we can have many experiments, and within one experiment, we can have many runs. Okay, so I've already run it, so the run is already there. So what happens now is that I submit with the estimator. So when I submit with the estimator, what it does, it takes everything what I have done out here, and it is pushing it to the experiment. So this actually, it takes a lot of time. So I've already run it. So let's go back here. So this is a run which is completed. If you go back here, the run has a lot of things. The run has got metrics, images, outputs, and logs. So what happened is that internally, it, you see, I wanted to do this spacey.load encore LG. All these things are there, which is there in the code out here. It is being run. So all these things are run here. So I can see the log out here. So this is the run. So one good thing is that whenever you are running, you can see all these things out here. After you have done the run, then what you can see is the metrics. And after you have done it, see, I have got this pickle file, right, which I have created out here, the spacey questions.pickle. Now, what I want to do is that I want to save it in my workspace. So what I do is that I register the model and I save it in my workspace so that I can use it later. So what I do is that if I go back to my workspace, I have registered it, and so you see that it is registered. See the traceability? The model is being created by this experiment, this run. So everything is traceable. If I go to this run, I can go back here. So everything is traceable. So this completes the training part of it. So my training is complete. Now suppose this is a very fantastic recommendation model that I have done. What I need to do is that I need to expose it to the whole world so that everybody can use it. So what I do is that there is called something called an inferencing part. So what better thing to do is to deploy this model into an AKS cluster, an Azure Kubernetes service cluster. So this is very interesting, right? So this is where the machine learning engineering is being so good that now we have done all the modeling, I have done all the recommendation work. Now I want the other people to use it. So let's use the power of Azure to push it to the outside world by pushing it to Azure Kubernetes service. So what we will see that. So this part is done. So my data scientist has already done everything. This is a part of the data scientist, and now somebody like a machine learning engineer or a data scientist who is well versed in inferencing can help in doing this. So how do we do it? So this is the next part of it. So here what I am doing is that the inference script is very simple. So inference script here, you see, the first it is composed of two blocks, the init block and the run block. What is the init block? The init block is loading the model. It is loading the model. So it is doing spacey questions model. So if I go back here to my models, this is and I am loading it here. And this is what it is doing. It is just loading. It is called when the service is loaded. And this is when the request is received. So what it does is that it gets the data, and what it is doing is that spacey questions, which is also pickle loaded here, spacey questions, which is there. And let me see whether I have. Okay, the spacey questions is out here. So the spacey questions is here. So I can load it. And then what I do is that, and what I'm doing is that I'm doing it from the model path. I'm loading the spacey questions. This is a model path. From the model, I am loading the spacey questions here. And then for the question that I am asking, I am creating a vector. So if my question is something like, I want to be a data scientist, what should I study? So for that, I am making a vector of 300 features. And then I am doing a cosine similarity with all of the questions. So what would happen is that for a question that is being passed, so it will calculate the cosine similarity for all the questions that I have in my repository, and then it will find the cosine similarity, and I am passing the predictions here. So we will see of how it happens. So again, here it is the dependencies for the inference script. So here also for the environment, we require scikit-learn, spacey, and pandas. We are creating the environment file. And here we are doing the inference config, which is basically what it is doing. It is combining the code, which is out here, the score.py, which is out here, and it is combining them into an inference config. Now I need a compute, right? So this compute, what I am saying is that I am provisioning an AKS cluster. An AKS cluster is being provisioned here. So I can see my AKS cluster. If I go to compute, you see my compute cluster is already there, the standard D2V2. The inference cluster is an AKS cluster. So if I go here, if I go to the AKS cluster, it's already done because it takes a lot of time to spring up. You can see this is my AKS cluster, which is here. So I'm provisioning an AKS cluster. So this AKS cluster is here. And if I go to services and ingress, we will see this, what we are doing. Now I am using a CPU 1 core, memory 1 GB. That is fine. And then I'm deploying it. So it is being deployed as a service. So what is the name of the service? We know that a Kubernetes cluster will have a service. The service name is Reco Service 3. If you go to the cluster, where is the cluster? You see this is a cluster. The Reco Service 3 service is there. Okay. So what I do here is, after it is done, I would get the scoring API. So the scoring URI is here. So it is this. Let us see whether it matches with some of the URIs out here or not. The cluster IP. Anyways, how it is. So I think it is getting it from somewhere. Oh, this is external IP. Okay. That's the thing. This is external IP, right? 52.154.45.54. So if you're familiar with this Kubernetes, right, it exposes an external API. So that is what it is coming out here. And then I'm getting the service keys, the primary key, and then I push in my question. So what is the question? I want to be a data scientist. What should I study? So it goes in and executes the code out here. The cosine similarity here. And what it does is that it gives off a response. Okay. So I am, so this response, what we will do is that we are trying to find out. So this is an index, right? So this index, I'm sorting the result, which has got the highest index. Okay, so this one is the highest thing. So I asked that how do I want to be a data scientist, what should I study? So the best answer is like this. Hello Chong Ji. See, this was answer given. I'm not a data scientist, but I think I can give you. Nowadays, an increasing are requiring blah blah blah. What it is saying, computer language, managing databases, and all these things. And then the second best answer, what it is saying is that you should search for algorithm videos, you should know about data structures and real cases and all these things. The next answer that it is saying that it is going into software engineering and doing all these things. So basically, it is giving you from the knowledge base what should you study. So this is a recommendation engine, a very simple recommendation engine using text data. So I will take a pause and see if there are any questions. So let me jump over to the questions if there are any.
Yeah, we have a question.
Yes, Ramesh has. Based on what values are computed for each of the 300 features. So what happens is that, Ramesh, that this spacey word embedding is based on glove. Okay, glove has been trained. Glove word embedding, I think it has been trained um, by Stanford. Okay. And what they did is that they have trained on a huge corpus of databases, words. Okay. They have trained on a huge corpus. So that is the basis of how they are doing it. So here it is a 300D vector common crawl. So this is how they have done. If you are interested, please do read Glove. So this is how they are training it and they are getting these vectors. Another thing that if you are very interested, now more advanced things have come. That is some transformers and everything. So they will have much more better accuracy. So please, if you are interested, go ahead and have a look at it. Yes, it is like Jainism. That's correct.
And I think as of, yeah, 1 second. Vanilla has
Yes,
another
yes.
question.
Is glove like Jainism? Yes, that's correct. It's like Jainism is also similar to that actually.
Okay. So if you have any other questions, please do post, guys. I think
Yes, yes. Hmm.
as of now, we don't have any other questions.
Yes, if you are really interested, please go ahead and try this competition. It is so you can always go ahead and try the other which have already been done, and there are lots of very innovative solutions which is there. So please try out and try things, and more so, I would encourage you is that. Mm. Now, because when this was there, not when this transformer was not there, so it would be nice if you can use some transformers which are much more advanced than the glove, and you can see of how good it is.
So, guys, we can hold up for a few more seconds. If you have any questions, please do post. And Ganguly, if you could switch to the other tab. Right now, it is showing the private chat. If you jump onto the comments tab, you could see the questions being asked in the YouTube chat. Yeah. Yeah, you have answered whatever the questions has been posted. uh, yeah.
Oh, I was speaking on mute. So I must thank
Okay.
you that some people have taken their time out in a Saturday evening to listen to me. I think it is very nice of you. So thank you for that. And one thing that I want to share with you is
Guys, please hold on. I think we lost Ganguly. He'll be back soon. So, meantime, if you have any questions, please do post. And if you want any specific topic to be discussed in some upcoming sessions, please do post about the topic as well. We'll find the best speaker, um, and do make it as a session as well. And Vanilla, I think just hold on a few minutes. Once Ganguly is back, I'll post this question. Okay, I think there should be an internet outage at Ganguly's site. Apologize, guys. So Vanilla, I'll make sure that the question is getting answered in the YouTube chat itself, or else I request you to post this question in the meetup group, the respective event, and we'll just make sure it is getting answered. Thanks everybody for joining today, and thanks Ganguly as well for taking his time to present this talk. So, with that, I'm ending the session. See you all in the next session, guys. Bye bye.